Okay, so page 580, number 1. Find the gravitational force between the Earth and the Sun. And then in brackets it says see Appendix B, physical constants and data. And that's so you can get the mass of the Earth, the mass of the Sun, and the radius between them. Okay, when you look it up, the mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the Sun is 1.99 times 10 to the 30th kilograms. And when you look up the radius, you'll see two of them there. One is the mean radius of the Earth's orbit, and the other is the mean radius of the Earth. So first, the word mean just means average, because it's not quite the same all the way around. Mean radius of the Earth is the radius from the center of the Earth out. That's the mean radius of the Earth. Okay? And usually we use a little r to designate that. Mean radius of the Earth's orbit will be from the center of the Earth to the center of the Sun. Okay? So you don't have to add the r's in, the little r's in. And this distance we usually call a capital R to denote that it's the radius of orbit. Okay, so radius of the Earth itself would be a small r, radius of the Earth's orbit would be a big R. If we're looking at the Earth orbiting around the Sun, then we want the capital R. And so it's going to be 1.49 times 10 to the 11th meters. And then you're just going to do Fg is equal to G m1 m2 over, and I'm going to put a capital R here to remind me I'm using the radius of the Earth's orbit. And if you don't do that, it's not going to be wrong. It's just to try to not get confused of what's a little r and what's a big R, what's orbit and what's just from the center of the Earth out. So G is 6.673 times 10 to the negative 11. Newton, whoops, be good if I get my units right, meters squared per kilogram squared. One mass is 5.98 to the 24th kilograms, and the other is 1.99 to the 30th kilograms. And then that is over the R, 1.49 times 10 to the 11th meters, and it's squared. The most common mistake, you write it down but forget to square it when you're typing it in your calculator. If you do type it in right, you get 3.577 times 10 to the 22 newtons for number 1. That is the gravitational force of attraction between the Earth and the Sun. Number 2, find the gravitational force between the Earth and the Moon. So again, you have to go to that same chart in the back on page 955. Mass of the Earth is 5.98 times 10 to the 24th kilograms. Just so that doesn't mess anybody up. That's not really a decimal there. Mass of the Moon is 7.36 to the 22 kilograms. And again, when you look at the radii, you'll see a mean radius of the Moon and mean radius of the Moon's orbit. You want the radius of the Moon's orbit. You want the one that's 3.84 times 10 to the 8th meters. And it's already, center to center is already added in. It's not just from the outer edge to the outer edge, okay? So when it's radius of orbit, you don't have to add the anything to it. It's already done for you. So Fg is equal to G m1 m2 over r squared. So Fg is equal to 6.673 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth 5.98 to the 24th kilograms. Mass of the Moon 7.36 to the 22 kilograms divided by the radius of orbit squared 3.84 times 10 to the 8th meters squared. And when you do this, you should get 1.992 times 10 to the 20th newtons for the gravitational force of attraction between the moon and the Earth. Number 3, how far apart, so you're looking for R, how far apart would you have to place two 7-kilogram bowling balls? So M1 equals M2 equals 7 kilograms. In order to have the gravitational force of attraction, the Fg, to be 1.25 times 10 to the negative 4 newtons. Okay, so you're rearranging Fg equals G M1 M2 over R squared for R squared. So R squared is equal to G M1 M2 over Fg. So 6.673 to the negative 11 Newton meters squared per kilogram squared times 7 kilograms times 7 kilograms divided by 1.25 times 10 to the negative 4 newtons. Remember, what you're going to get is going to be R squared, and you're going to need to take the square root. So R squared is 2.615 to the negative 5 meters. And when you take the square root, R is 5.115 times 10 to the negative 3 meters. Or if you want it, R is 0.5115 centimeters. The reason I wrote it as the second, as in centimeters, is because of the last part of the question, which says, would it be possible to place them at this distance? Why or why not? Remember, this is the distance from the center of one bowling ball to the center of the other. Well, if you're going to place them 0.5 of a centimeter apart, so from the center of one to the center of the other is a half a centimeter, these bowling balls are going to be mighty, mighty tiny. I have a hard enough job hitting the bowling pins with a regular size ball. Please don't invite me to bowl with you if you're using balls that are that small. So no, it would not be possible. Number 4, find the gravitational force between an electron and a proton. So you need to go back to the chart and find the mass of the electron is 9.109 times 10 to the negative 31 kilograms, and the mass of a proton is 1.673 times 10 to the negative 27 kilograms. Okay, so that's given on the chart as well. And then it says that are placed 5.3 to the negative 11 meters apart. So R is 5.3 times 10 to the negative 11 meters. And for those of you in Science 12.2, you might actually recognize that as the radius of a hydrogen orbit, the n equals 1 orbit. So these numbers are actually accurate. So you're looking for Fg equal to G M1 M2 over R squared. So 6.673 to the negative 11 Newton meters squared per kilogram squared times 9.109 to the negative 31 kilograms times 1.673 to the negative 27 kilograms. And all of this is going to get divided by 5.3 to the negative 11 meters squared. Do not forget to square it. And you should get, you're looking for Fg, you should get 3.6202 to the negative 47 newtons. So not a very big force at all. But that's because they're not very big. Right? So you don't need a force like that you would need if you were trying to hold a person in orbit. If you're trying to hold an itsy-bitsy little electron, it's okay that the force is tiny. Number 5, on Venus, a person with a mass of 68 kilograms would weigh 572 newtons. That is your Fg that they're giving you. Find the mass of Venus from this data given the planet's radius. So the R is 6.31 times 10 to the 6th. And notice I'm writing it as a small r because you're on the planet, you're not orbiting it. So it's really just the radius of the planet. And so you're looking for the mass of Venus. So M of Venus will equal R squared Fg over Gm. Gonna run out of time. Shoot. And you should get 5.019 to the 24th.